We'll start our discussion about inverse functions by talking about one-to-one functions, because the characteristic of a one-to-one function is that its inverse is a function. But math is built on definitions, and so let's look at a definition for one-to-one functions. F is a one-to-one function if f of x2 is different from f of x1 whenever x2 is different from x1. In other words, if I have two different inputs, then they should map to two different outputs. Another way to put that would be that outputs could match, but only if inputs match. And we'll see what this means as we work through this section. First, let's look at some visual characterizations. Here we have two functions. One is on the left we have a cubic function, and then on the right we have a squaring function. And we can see that the cubic function is one-to-one. And we all remember, I'm sure, that the graph of a function must pass the vertical line test. The graph of a one-to-one function must pass the horizontal line test. That is, a horizontal line will intersect the graph at no more than one point. On the right, we see for the parabola, a horizontal line would intersect at 2 points. And if the horizontal line intersects at 2 points, then that means I have two matching outputs for inputs that don't match. So that's how it violates the definition of a one-to-one function. We can, however, consider just a part of the graph. And here we're looking at on the right, that part of the graph. And we can say that by restricting the domain so that we're only considering this set of x such that x is greater than or equal to 0, so the right portion of it, we have a piece that is one-to-one. Again, we care about one-to-one because then the inverse is itself a function. The reason for that is that the inverse of a function reverses inputs and outputs. So suppose we have a function f that maps a domain into a range. Then we have, say, one input value of x1, and it would map to an output value f of x1, which we can call y1. The inverse reverses the process. And so we can say that the inverse maps y1 to f inverse of y1, and that's what x1 is. Graphically, the inverse of a function is a reflection. If I have a function f, and I'm going to put a point on the function for reference, ab, then its inverse is a reflection about the line y equals x. And so in this case, would look like that. And the point AB would be manifest on the inverse, so here's f inverse, as BA. And so we can see from AB to BA that the inputs and outputs have been reversed. Math is built on definitions, and they lead us to theorems. And we have here a theorem. If f is one-to-one and continuous on the closed interval from a to b, then f inverse is also continuous. First, let's remind ourselves of what continuous means. A function f is continuous at a point a if the limit as x approaches a of f of x is equal to f of a. In other words, the limit value has to equal the function value, which means the function value has to be defined, and that's one of the reasons we're looking at closed interval here. Now, theorems are proved, and that's how math people know that they're right. What I'm going to give you now is not quite a proof. The full proof is in an appendix. We're going to start by saying if f is one-to-one, then that means that f is either increasing or decreasing. In other words, f can't change direction. Well, the graph of it can't, because if we have a graph that changes direction, then we end up with violating one-to-one. So let's see why this statement should be true. Here we have a diagram, and suppose we have a function that maps x1 to f of x1, so here's a point there, and x3 to f of x3, and so there's another point there. And I've drawn some dashed segments here so that we can help with the visual. Now what we're going to do is we're actually going to presume the opposite of f is increasing or decreasing. We're going to assume that it does end up changing direction somehow, and then see that that's going to be a problem. And for purposes of having just something to look at and think about, we're going to, right now we're assuming that f is increasing. But suppose we have an output for x2 that doesn't lie between the outputs for x1 and x3. In particular, suppose f of x2 is greater than f of x3. If f is continuous, then by the intermediate value theorem, there exists a c between x1 and x2 such that f of c is equal to f of x3. Let's unpack that in a minute, but first I've given you some shorthand. This arrow here means it's an if then, which also means implies. The backwards uppercase E, there exists, or there is, and then the curly backwards little e looking thing is such that. Now, to unpack this statement, what we've just said is if x2 is up here and if f is continuous, then the only way to connect x1 f of x1 to x2 f of x2 is to cross this dashed line, which is at the same y value as f of x3. And so the intermediate value theorem says there would be some point here, c, where the output for c matches the output for x3. But if c doesn't equal x3, then those outputs cannot match. And so this contradicts that f is 1-to-1. And we could make a similar argument for a function that was decreasing, or if f of x2 was below f of x1. Now back to our original proof here, and it's about the continuity of f inverse. We're going to suppose f is increasing. Then, for every epsilon greater than 0, such that the interval x0 minus epsilon to x0 plus epsilon is contained in AB, f maps that interval x0 minus epsilon to x0 plus epsilon into f of x0 minus epsilon to f of x0 plus epsilon. Don't worry, we are going to see a diagram. First, this upside down a here, more math shorthand for every. Now let's see this diagram. So we're going to identify an interval that contains an x0 value. And this interval is going to be x0 minus epsilon to x0 plus epsilon. So we're subtracting and adding a small amount to x0. And here the statement is that that interval is contained in an interval from a to b. So that's what that looks like there. Now the statement here that f maps that interval into another interval gives us the idea of another number line here. And on this number line here, I've identified a y0, and then f of x0 minus epsilon, f of x0 plus epsilon. And I've intentionally made this an asymmetrical interval because there's nothing that says that this has to map to a symmetric interval about y0. But the idea here is that x0 minus epsilon is mapped to f of x0 minus epsilon, likewise for x0 plus epsilon. And f maps the upper line to the values to the lower line values. And to be abundantly clear here, x0 minus epsilon and x0 plus epsilon are both within, are epsilon away from x0. Now, if epsilon sound familiar, then it will probably make sense to you that we're going to consider some delta values. You see, we're looking at epsilon and delta because here, in our definition for continuous, we have a limit statement, and as you know, epsilon and delta tend to show up when we're thinking about limits. Definitions anyway. So we're going to identify these intervals on the y-axis here as delta 1 and delta 2. Ease of writing, we're going to let simply delta equal the minimum of delta 1 and delta 2. It's not just for ease of writing, but that's one of the effects. So whichever of these two, delta 1 and delta 2, is smaller, we're going to label that delta. And we can see here that the smaller of the two, and the way I've drawn this, is on the left, so there's delta. And then reproducing that on the right will give me a symmetrical delta neighborhood about y naught. By selecting delta to be the smaller of the two, delta 1 and delta 2, we can say that the interval y naught minus delta to y naught plus delta is contained in the interval from f of x naught minus epsilon to f of x naught plus epsilon, the y interval that we started with. Because f is increasing, all of the y values in the bigger interval on the y-axis are mapped from x values within the interval on the x-axis. By assumption, f is 1 to 1, and therefore an inverse exists. And so f inverse will map elements on the y-axis into elements on the x-axis. And in particular, f inverse maps y naught minus delta to y naught plus delta into x naught minus epsilon to x naught plus epsilon. So all the values in the pink range down here came from values within this interval on the x-axis, so the inverse maps into that interval. Another way to put what we just wrote is for epsilon greater than 0, there exists a delta such that if y minus y naught in absolute value is less than delta, then in absolute value f inverse of y minus f inverse of y naught is less than epsilon. If you were to refer back in the textbook to the definition of a limit, then you would see we just satisfied it. So then we can conclude that the limit as y approaches y naught of f inverse of y is equal to f inverse of y naught, and that satisfies the definition, had a wrong symbol there, that satisfies the definition for continuous for f inverse. And that's essentially an outline of the proof that is in the appendix.